Hello everyone, welcome back. If you've been following this channel, we've gone deep on DSA, low-level design, and high-level design. We've always focused on truly understanding things, not just surface level. And that's exactly what we're going to do with AI. This is the start of our AI series, and I promise you, by the time this series is done, when someone says transformer architecture or gradient descent or loss function, you won't just nod along. You'll actually know what it means. Let's get into it. Most of us think AI is something that was invented in the last 5 or 10 years. ChatGPT came out, everyone lost their minds, and suddenly AI felt brand new. But here's the thing, the foundation of AI goes all the way back to the 1940s. Researchers back then were already asking, can we build a machine that thinks? Can we model how the human brain works? And the answer they came up with was, let's try to replicate a neuron. So, what is a neuron? In your brain, a neuron is a cell that receives signals from other neurons. And if those signals are strong enough, it fires. It sends its own signal forward. That's it. Receive signals, decide whether to fire. Researchers thought, what if we could do this mathematically? What if we could build an artificial version of this? And that's how artificial neural networks, ANNs, were born. Now, at this point, don't worry about the math inside a neuron. We'll get to that very soon. For now, just hold on to the idea. A network of artificial neurons connected together, passing signals forward. Each neuron takes some inputs, does a small calculation, and passes a result to the next layer. That's an ANN at its core, and these networks were genuinely useful. If you had a table of data like house features and prices, an ANN could look at thousands of examples and learn to predict prices on new houses. Great. But there was one big problem. ANNs had no sense of time, no memory. Let me give you an example. Imagine I give you the sentence, the food was not good, but the service was amazing. Now, to understand this sentence, you need to remember what came earlier. Not good refers to food. Amazing refers to service. You can't understand word 10 without remembering words 1 through 9. But an ANN treated every word as completely independent. It had no way to carry context forward. For language, for speech, for anything that unfolds over time, this was a serious limitation. So in the 1990s, researchers invented recurrent neural networks, RNNs. And the key idea was simple. Let's give the network a memory. After processing each word, the network keeps a small summary of what it has seen so far and carries it forward to the next step. Think of it like reading a book. As you read each page, you don't forget everything from the previous pages. You carry context with you. RNNs tried to do exactly that. And RNNs worked for short sequences. But here's where it got tricky. Imagine you're reading a very long book, 500 pages. By the time you reach page 500, you've mostly forgotten the details from page 1. RNNs had the same problem. The further back a piece of information was, the harder it became for the network to hold on to it. The memory faded over time. So in 1997, researchers came up with a smarter design, long short-term memory networks, or LSTMs. And the clever idea was, instead of having one blob of memory that slowly fades, let's build a system with gates. Think of gates like decisions. At each step, the network asks 3 questions. What from my past memory is still relevant? Keep that. What is no longer useful? Forget it. What new information just came in? Add that. It's like how you naturally read a book. You remember the main characters and the plot twists. You forget the exact words on page 47. You selectively remember what matters. LSTMs could do this, and they dominated the field for years. But even LSTMs had a problem, and it was a practical one. They were slow. Because memory is passed step by step, you can't process word 2 until word 1 is done. Word 3 has to wait for word 2. It's like an assembly line where each worker waits for the one before them. If you're training on millions of sentences, this becomes very slow. And then in 2017, everything changed. A team at Google published a paper with a bold title, Attention is All You Need. And they proposed a completely different approach, the transformer. Instead of processing words one at a time and passing memory forward, the transformer looks at all words simultaneously. Every word looks at every other word at the same time and figures out which ones are most relevant. Going back to our sentence. The food was not good, but the service was amazing. The word amazing can directly look at service and say, these two are connected. The word good can directly look at food. No waiting, no fading memory, just direct attention between any two words. And because everything happens in parallel, training became dramatically faster. GPT, Gemini, Claude, all of these are built on the transformer. This is the architecture that made the AI revolution happen. We'll do a full dedicated video on how transformers work later in this series. For now, remember the story. Each architecture tried to solve a problem the previous one couldn't. NNs had no memory. RNNs had fading memory. LSTMs had better memory but were slow. Transformers threw out memory entirely and replaced it with attention. And that changed everything. Now, before we go deep into how neural networks work internally, let me show you the bigger picture first. The end-to-end process. What does it actually look like to solve a real machine learning problem? And to keep this concrete, we're going to use a single example throughout this entire video, predicting house prices based on the area in square feet and the number of bedrooms. Simple, relatable. Let's walk through it step by step. Step 1. Define the problem. What exactly are we trying to predict? In our case, we want to predict the price of a house, a specific number in rupees. When the output is a number, we call that regression. If instead we were predicting a category, like is this house expensive or affordable, that would be called classification. Knowing this upfront matters because it shapes every decision you make later. Step 2. Collect and prepare data. Imagine you've scraped 10,000 house listings from a real estate website. Now, real data is never clean. Some listings have missing information. Maybe the number of bedrooms isn't filled in. Some have obvious errors. A 1 square foot house listed for 10 crore. You need to clean this, handle the missing values, remove the bad data, and also make sure your inputs are on a comparable scale. Because area in square feet can be in the thousands, while bedrooms is just a single digit number. That mismatch can confuse the model. This cleanup step takes up most of the time in real projects, more time than building the model itself. Step 3. Split your data into a training set and a test set. Typically 80% for training, 20% for testing. And the model never sees the test data during training. Why? Here's a simple analogy. Imagine a student preparing for an exam. If the student somehow gets access to the exact questions before the exam, they'll memorize the answers and score 100%. But that tells you nothing about whether they actually understand the subject. The test set is the unseen exam for your model. If the model performs well on data it has never encountered, that's genuine learning. Step 4. Define your neural network. How many layers? How many neurons? We'll spend a lot of time on this. Step 5. Train the model. You feed the training data in, the model makes predictions, you check how wrong it is, and you update it to be a little less wrong. Repeat thousands of times. Step 6. Test and deploy. You evaluate on that held out test set. If performance is good enough, you ship it. Maybe as an API, someone sends in area and bedrooms and gets back a predicted price. That's the full loop. And notice, steps 4, 5, and 6 are where all the interesting stuff happens. That's what the rest of this video is about. Alright, let's now get into the heart of this video. How does a neural network actually work? Let's start small. A single neuron. You know how in your brain, a neuron receives signals from other neurons? It collects all those incoming signals, and if the combined signal is strong enough, it fires. It passes something forward. An artificial neuron does the same thing, but with numbers. It takes a set of inputs. In our house example, that's area and number of bedrooms. It multiplies each input by a number called a weight, which controls how much that input matters, adds them all up, adds one more number called a bias, and then passes the result through something called an activation function, which decides what the output of this neuron is. We'll go deep on what weights, bias, and activation functions mean very shortly. For now, just hold the picture. Inputs come in, get combined, output goes out. Now, a neural network is just thousands of these neurons, organized into layers. The first layer is the input layer. This just holds your raw data, area and bedrooms, no computation here. Then you have one or more hidden layers. These are the layers where the actual learning happens. Each neuron in a hidden layer takes all the outputs from the previous layer, does its computation, and passes its result forward. And finally, the output layer gives you your prediction, the house price. Now here is the most important intuition in all of deep learning, and I want you to really sit with this. Each layer builds on top of the previous one. Each layer understands something slightly more complex than the last. We call this abstraction. Let me explain this with a different example. Image recognition. Suppose we're training a network to recognize human faces in photos. Think about this. What is the absolute simplest building block of any image? An edge, just a line between a light area and a dark area. The very first hidden layer learns to detect edges, horizontal edges, vertical edges, diagonal ones. Nothing fancy, just edges. The second layer takes those edges and combines them into something more complex: corners, curves, simple shapes. The third layer takes those shapes and starts forming object parts, something that looks like an eye, something that looks like a nose. And the deeper layers put all of that together and say, yes, this is a face. Now, here's the part that should blow your mind. You never programmed any of this. You didn't write any code that says detect edges in layer 1 or look for noses in layer 4. The network figured all of this out entirely on its own, just by looking at thousands of labeled photos of faces. The hierarchy of understanding emerged automatically from training. That is the power of stacking layers. Now, I want to tell you something that will change how you think about neural networks. There's a mathematical result called the universal approximation theorem. And in plain English, it says this: a neural network, given enough neurons, can approximate any function. Any function. Now, what does that mean? A function is just a mapping. Inputs go in and output comes out. The price of a house is a function of its features. The sentiment of a sentence, positive or negative, is a function of the words in it. Whether a medical scan shows a tumor is a function of the pixel values. Whether a credit card transaction is fraud is a function of dozens of variables. The theorem says a neural network can learn all of these mappings. Any relationship between inputs and outputs, however complex, can be captured by a neural network with enough capacity. That's why the same architecture powers a house price predictor, a language model that writes code, a system that folds proteins, and a car that drives itself. One framework, unlimited applications. Now here's something interesting. Technically, even a single hidden layer is enough. If it has enough neurons, it can approximate anything. But in practice, we use many layers. Why? Because depth is efficient. A deep network can represent complex things using far fewer total neurons than a wide, shallow one. Each layer builds on what the previous one learned, so you get more for less. More importantly, the hierarchy of understanding that we just talked about, edges to corners to faces, that only emerges naturally from depth. More layers, more neurons, more expressive power, more ability to model complex patterns in the world. This is why we call it deep learning. And this is why when people say a model has billions of parameters, they're essentially saying this model has an enormous capacity to understand the world. All right, while discussing about artificial neural networks architecture, I kept saying the network learns weights. But what does that actually mean? Let's make it completely concrete. Start with the simplest possible model. One input, area. One output, price. The relationship looks like this. Price equals W times area plus B. That's it. One weight W, one bias B. Say after training, the model found that W equals 500 and B equals 50 lakhs. Let's plug in a house with 1,000 square feet. 500 times 1,000 plus 50 lakhs. That gives us 55 lakh rupees as the predicted price. Now look at what was doing. W equals 500 means for every extra square foot of area, the price goes up by 500 rupees. On the graph, W is the slope of the line. What happens if W were 1,000? The line gets steeper. Price increases much faster with area. What if W were 100? Much flatter. Area barely moves the needle on price. What if W equals 0? The line is completely horizontal. Area has absolutely no effect on price. The feature is useless to this model. And a negative W would mean as area increases, price drops, which is clearly wrong for houses. So the weight tells the model how much each input matters. And the model's job during training is to find the right value of W that makes the line fit the actual data as closely as possible. Now in a real model, you have multiple inputs. Price equals W1 times area plus W2 times number of bedrooms plus B. Each input gets its own weight. A trained model might find U1 equals 400 and U2 equals 20,000. That's telling you each square foot adds 400 rupees and each additional bedroom adds 20,000 rupees. These numbers are not set by you. The network learns them entirely from the data. Real-world relationships are almost never straight lines. Let me show you what happens when they're not. Consider we want to predict whether a student passes or fails an exam based on how many hours they studied. The output here is binary, 0 for fail, 1 for pass. Now, can we use a straight line for this? No. And here's why. A straight line can go below 0 and above 1. But probability can never be below 0 or above 1. A 40% chance is 0.4. A 90% chance is 0.9. There's no such thing as a minus 20% chance. So a straight line is the wrong shape for this problem. What we need is a curve that stays between 0 and 1. something that starts near 0 for students who barely studied, rises smoothly, and flattens near 1 for students who studied a lot. That S-shaped curve is called the sigmoid function, and it's one of the most important shapes in machine learning. Now the weight W controls how steep that S-curve is. A large W means a very sharp transition. Students clearly pass or fail with almost no gray area. A small w means a gradual slope. The model is uncertain about the threshold. Training finds the right W. But now, here's where bias becomes really important. Without a bias term, that S-curve is always centered at 0 hours of study. It's fixed in place. But think about reality. Maybe students only start reliably passing after studying 5 hours. The transition point isn't at 0, it's at 5. Without bias, the model can't represent that. It's stuck. Bias is what lets you shift the curve left or right to wherever the data actually lives. So here's the key thing to remember. And I wrote this on the board. The weight controls the shape of the function. The bias controls its position. You need both. Without weight, every neuron behaves the same way regardless of input. Without bias, every neuron is stuck at a fixed position regardless of the data. Together, they give each neuron full flexibility to be exactly what the data needs it to be. And every single neuron in the network, across every layer, has its own weight and its own bias. Millions of them, all being fine-tuned during training. That's what it means for a network to learn. Now the big question, how does the network actually learn these weights and biases? How does it go from knowing nothing to making accurate predictions? At the very start of training, all weights are set to small random numbers. The network is essentially guessing. Its predictions will be terrible. And that's completely fine. Because training is the process of making it progressively less wrong, one small step at a time. The training loop has 4 steps, and these 4 steps repeat thousands of times, sometimes millions. Step 1, the forward pass. You take one training example, a house with 1,000 square feet and 2 bedrooms. You feed it through the network, through the input layer, through the hidden layers, all the way to the output. The network does its calculations at each neuron and spits out a prediction. Let's say it predicts 4 lakh rupees. Step 2, compute the loss. The actual price of that house is 5,50,000. The network was off by 1,50,000. The loss function gives us one single number capturing exactly how wrong this prediction was. We'll look at loss functions right after this. Step 3, backpropagation. This is where the network figures out who is responsible for the mistake. Think of it like a post-mortem. The prediction was wrong. Which weights made it go wrong, and by how much? Using some calculus under the hood, the network computes a gradient for every single weight. The gradient tells us, if I nudge this weight slightly, does the loss go up or go down? Step 4, update the weights. We adjust every weight in the direction that makes the loss smaller. Then we go back to step 1 with the next training example. Here's the intuition I want you to take away. Imagine you are blindfolded, standing somewhere on a hilly landscape, and your goal is to find the lowest valley. You can't see anything, but you can feel the slope under your feet. The strategy is simple. Always take a step downhill. Feel which direction the ground slopes down and step that way. That is gradient descent. The landscape is the loss surface. Every possible combination of weight values gives a different loss. The valley at the bottom is the set of weights that makes the model most accurate. The gradient is the slope. It tells you which direction is uphill. So you go the other way. And slowly, step by step, you find the valley. The learning rate is the size of each step. Take 2 larger steps and you overshoot the valley and end up on the other side. Take 2 smaller steps and it takes forever to get anywhere. Now we understand that the training loop computes a loss, how wrong the prediction is. But how exactly do you measure wrong? That's what the loss function decides. It tells us how are we measuring the loss. And the choice matters a lot. Let's look at the 2 most common ones. For example, when you're predicting a number like house price, which is a regression problem, we use mean squared error. Take the difference between the actual price and the predicted price, square it and average that across all your training examples. Why square it? 2 reasons. First, squaring makes everything positive. Being off by minus 50,000 is just as bad as being off by plus 50,000. Squaring removes the sign. Second, and this is the important one, squaring punishes big mistakes far more than small ones. If you're off by 10, the squared error is 100. If you're off by 50, the squared error is 2,500. A 50 times bigger mistake becomes 250 times worse in the loss. The model is strongly pushed to avoid large errors, which is exactly the behavior we want. For classification problems, when you're predicting a category like pass or fail, we use cross-entropy loss. And the intuition here is really elegant. This loss function specifically punishes confident wrong predictions. Here's an example. Suppose your model says, I am 99% sure this student passes, but the actual answer is fail. That's the worst kind of mistake. Completely wrong and completely confident. The cross-entropy loss here is enormous. The model gets heavily penalized. Now suppose the model says, I think there's about a 60% chance this student passes. And it's wrong. The model was uncertain, and it was still wrong, but it wasn't overconfident. The loss is much smaller. What this teaches the model over time is to be honest about its uncertainty. If you're not sure, say you're not sure. Don't pretend to be confident when you're not. And this is why choosing the right loss function matters. It's what drives the entire training process. Use the wrong one, and your model will optimize for the wrong thing no matter how long you train. MSE for regression, cross entropy for classification. Let's take a step back and look at everything we covered today. We started with the evolution, how AI went from a simple artificial neuron in the 1940s to recurrent networks that could handle sequences, to LSTMs that could remember over long distances, to transformers that changed everything in 2017. We then walked through the end-to-end process of solving a machine learning problem, from defining what you want to predict, cleaning your data, splitting into train and test, all the way to deploying a model. We understood how a neural network is structured, layers of neurons, each one building a more complex understanding than the last. We saw how even recognizing a face is really just edges becoming corners, becoming shapes, becoming parts, becoming a face, all learned automatically. We covered the universal approximation theorem, the reason a neural network can, in theory, model any relationship in the world. We made weights and bias concrete. Weight controls how much an input matters. Bias gives the model the freedom to position its function where the data actually lives. We walked through the training loop, forward pass, loss, backpropagation, gradient descent, and understood that training is just walking downhill on a loss landscape, one small step at a time. And we looked at loss functions, MSE for regression, cross entropy for classification, and why the loss function is the engine that drives all of learning. That's it for this video. If this content helped you, subscribe. Every video in this series builds on the last. See you in the next one.